Okay, so we are going to continue with the chemistry of life. And just to give you a quick reminder that we were looking at Unit 1 and the structure of water and hydrogen bonding. And we had gone through all of the characteristics of water based upon water's polarity and able to be hydrogen bonded. And we left off with it being the solvent of life, being able to dissolve other polar molecules and ionic substances, but not nonpolar things. All right, so that's where we're going to continue on. And so actually what we're going to write next is kind of goes with the solvent of life. All right, so we had put a bullet here where water does not dissolve things with no charge, and we're going to start out with another bullet to go underneath there. So let's write this. So I'm going to write another bullet, and we're going to relate this to inside a living thing. So chemical reactions in cells depends on collisions of molecules. So when once a reaction occurs, those molecules that are going to react, they're bouncing around in a cell, and they need to be able to collide in order for a reaction to occur. So therefore, it depends on the collision of molecules whether or not the reaction will occur, and therefore the concentration of solutes in aqueous solutions. Since we're talking about water, aqueous solutions are water-based solutions. All right, so that's what you would put there, they're water-based solutions if you don't know what aqueous means. And so the higher the concentration, the more molecules you have in a given area, and therefore the more collisions that you will have, and therefore the more chemical reactions you would have. All right, so a couple of things about that. The number of molecules are usually measured in something that we call moles, which you should have learned about in chemistry. With 1 mole being, do you remember the number? 6.02 times 10 to the 23rd molecules. So it's a measurement of how many molecules. Just like a dozen eggs, we have molecules are so small, so our measurement is very, very large. All right, so then when we talk about concentration of solutions, we usually talk about it in terms of molarity. So molarity is the number of moles of solute per liter of solution. So let me give you an example here. All right, so you have a beaker and you put in a liter of water, so it's a 1 liter beaker. You have your water, you put in 1 mole of a substance, and 1 mole of the substance happens to be its molecular mass. If you add up the mass of all the atoms in the molecule, that's its molecular mass. And so you put in 1 mole of it and fill up to a liter of water, and we would say that this collectively is a 1 molar solution. Capital M refers to molar, and so it's a 1 molar solution. And so, and it could be a 1 molar sucrose solution. If it's table sugar, we're putting a mole of table sugar in this, or it could be salt or whatever it may be. So a 1 molar solution, the liter has 1 mole in it, a 2 molar solution, that liter of water would have 2 moles of the solute in there. A 0.5 molar solution would have half a mole dissolved in the liter. And so this will come up later on about when we dissolve things in water and about the concentration, and that will be described in the concept of moles and molarity. And so I wanted to bring that up now since we're talking about water. This last concept about water that I wanted to discuss with you, and we're going to make this Roman numeral number 2. So Roman numeral number 1 was all about water being made from hydrogen and oxygen, and all about its molecular structure and characteristics. So Roman numeral number 2, we're going to say, is about what we call the dissociation of H2O. I'll say H2O molecules. Oops, I didn't leave myself a lot of room here. Molecules leads to acidic and basic conditions. So we're going to talk about acids and bases, conditions that affect living things. So let's talk about a property of water here in respect to acid and bases. So I'm going to put here letter A here. Water can separate into a hydrogen ion. A hydrogen ion is H+. So whenever you see H+, that's how we say that as hydrogen ion. And a hydroxide ion. Hydroxide ion is OH negative. So that's how you would say that. You could say OH negative, or it's a hydroxide ion. All right. So, and this is rare that this happens, but it can happen. And when it does, there are equal concentrations of H+ and OH negative. So we're going to say down here that water, therefore, has equal concentrations of H+ and OH negative ions because of this, because it breaks down equally into H+ and OH negative ions. So we would say in pure water, how we would write this is the H+ concentration. Concentration is represented by these brackets. And so H+ concentration, that's how we'd say that, is, or the hydrogen ion concentration is equal to the hydroxide ion concentration. So brackets around something means the concentration of that substance that the brackets are around. All right, so then let's move on here. Let's talk about then when those aren't equal. So when something is an acid or a base. So changes in concentrations of H+ and OH negative ions can have a big impact. Big impact on the chemistry of the cell. Which is why we're talking about it. All right, so let's talk about what happens when an acid is added. So underneath B here, I'm going to put 1. Adding an acid to water, what happens? It increases the hydrogen ion concentration. increases. And so how does that work? All right, so if something is acidic, instead of the H pluses and OH negatives being equal, if something is acidic, the concentration of the hydrogen ion is greater than the concentration of the hydroxide ion. So it's uneven. So I'm going to give you an example of adding HCl to water. And I'm going to do some color coding here so we can see more clearly. So let's see, let's do HCl in orange. All right, so HCl is one molecule, it's hydrochloric acid, and it's ionic. The H has a positive charge and the Cl has a negative charge, so so I'm gonna put those little charges on there. When HCl is added to water, it dissociates into the H plus, the hydrogen ion, and a chloride ion. So it comes apart. So let me illustrate that to you. Let's do blue for water. And I'm gonna show you, if you have just water, let's say I have a container of water, and water has equal concentrations of H pluses and OH negatives. All right, so I'm gonna make 2 of each to show that there's equal concentration. All right, so that's my pure water. If I were to add this acid, hydrochloric acid, into this, then what's going to happen is it will dissociate into the H plus and Cl minus. So let's draw that with our color. So I'm going back to the orange here. So you add the HCl into the water, and then HCl is going to be H plus and Cl minus. It dissociates here. So notice that before, all right, before I add the HCl and I had just water, I had, for OH negative, I had 2 out of the 4 ions, 1, 2 out of the 4 that were OH negative, and H plus, I had 2 out of the 4. All right, but now, now that I've added the HCl, it's no longer, that's no longer the case. So now instead of 4 ions, I have 1, 2, 3, 4, 5, 6. And when I look at now OH negative, I have 2 out of the 6 being OH negative, and I have for H pluses, I have 1, 2, 3 out of the, did I count that right? 1, 2, 3, 4, 5, 6. I did. Okay. And then I have, for H pluses, I have 3 out of the 6. So this is higher than this. So now they're no longer equal. My concentrations of each of them, they were equal. Now they're not. There is a higher concentration of H pluses because the HCl added H pluses into the mix. All right, so that's how an acid works. So let's look at now what a base does. So I'm going to put here a 2. All right, and let's say adding a base to H2O decreases the H plus ion concentration. So it works in the exact opposite way here. All right, so something that is basic, and comparing the H plus and OH negative concentrations, there's going to be, it lowers the hydrogen ion concentration, and the hydroxide ion concentration becomes higher. All right, so let's give I'm going to give you 2 examples of this. All right, so example 1 of this is with NaOH. All right, NaOH. This is, the OH is the hydroxide ion that has a negative, and the sodium has a positive. This is the ionic compound, and it breaks down into its associated ions, so Na plus and OH negative, when you put it into water. So again, to illustrate, this, let's see, I will use, I don't know, let's say purple for the base. I didn't color that yet. I forgot to color code the NaOH here, but let's say in your water you have equal concentrations of our ions, all right? And so that's what we talked about before, so 50-50. And then when you add NaOH, it's going to dissociate into Na and OH. And we said that a base is going to lower the hydrogen ion concentration. So if we look here, we have 1, 2 out of 1, 2, 3, 4, 5, 6. All right. And the OH is 3 out of 6. So therefore, the hydrogen ion concentration, the 2 out of 6, has been lowered than what it was. It was 50-50 between the two. And now the H plus concentration is lower than the OH negative concentration. That is one way that a base can work. The second way that a base can work, example 2, is by accepting H plus ions out of the solution. So let me give you an example here. NH3, NH3, if that comes into contact with an H plus ion, it forms an ion called NH4 with a positive charge. So let me illustrate that and what goes on with that in the solution. So in this case here, we have our water that has equal concentrations of H pluses and OH negatives. NH3 comes along, and NH3, I'm going to draw that in here. So NH3 has 3 H's coming off of it. The N is electronegative, so the N actually has a slightly negative charge, kind of like the oxygen in water. And so what happens is, I'm going to get a third color here just to show you what happens, is this negative charged nitrogen attracts one of these positively charged hydrogens. And when it does, it becomes NH4 with a positive charge. But what I want you to see here is that you did originally have 50-50 H pluses and OH negatives. I just now noticed that that looks like an H negative. It's supposed to be H positive. And when one of the H pluses are attracted to the NH3 and becomes NH4, now you have one less H plus in the solution, thereby lowering the hydrogen ion concentration. So both of these act as bases, they just act in one of two different ways. And that is what a base does. So now running out of room here, let's get another sheet of paper here and go on to continue on with the acids and bases. So notice here I put this as B, the changes in concentration, and talking about acids and bases. We're going to go now to C, all right, and talk about the pH scale. So the pH scale measures the hydrogen ion concentration, so I'm going to shorthand it like that with the brackets, and therefore how acidic or basic a solution is. So the pH scale, if you recall, all right, I'm not sure how much you remember from the pH scale, but we're going to go ahead and draw it. So here's the pH scale, just so that you remember. I'm going to draw it with a number line. Do you remember the highest and lowest pH? Lowest is 0. It goes from 0 to, do you remember the highest number? If you said 14 in your head, you would be right. All right. And so then 7 is smack dab in the middle. 7 is considered neutral. At 7, this is pure water. So what do we know about pure water? That at pure water, the H plus concentration equals OH negative concentration. All right, so that's what we know there. So then we can put on little lines for the numbers here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So close enough, not quite equal there. And then, so obviously this would go from 7 down to 0. So this would be 6, 5, 4, 3, 2, 1. These numbers here from 7 below represent something that's acidic. So if it has a number of 7 or below, it's acidic. So that means, again, the H pluses are higher or lower than the OH negatives. If you said higher, you would be correct. And then this way goes from 8, 9, 10, 11, 12, 13, and then 14. And this is basic. And in this case here, the H plus ion concentrations are lower than the OH negative concentration. All right, and that's what acidic and basic means. So, all right, and so I'm going to put here that it's figure 2.23 in your textbook shows you these some common things in real life. I'll just show it to you here real quick so you can see 0, you can see 1 is battery acid, 2 gastric, that's in your stomach, lemon juice, you can see vinegar and wine, rainwater, slightly acidic, urine are slightly acidic, pure water. Blood is just over 7. It's slightly basic, but very, very close to that 7. All right, and so then you can see seawater, milk of magnesia, which is a medicine for upset stomachs, ammonia, bleach, oven cleaner, and so on. So you can kind of see that. I like this picture because it draws what we just talked about, but also gives you a visual in terms of concentration of H pluses and OH negatives. All right, so that's for your reference when you look in your textbook to study and so on. All right, so let's talk about this pH scale, what the numbers mean. So I'm going to put a little asterisk here and say that each unit, that's each number on the pH scale, represents a 10-fold increase or decrease in hydrogen ion concentration. Okay, let's talk about what that means. All right, so we said that as you go this way, you get a higher and higher H plus ion concentrations. So when you go from a pH from 7 to a pH of 6, a pH of 6 has 10 times more hydrogen ions than a solution at a pH of 7. So then the difference between a 7 and a 5 then would have how many times more H pluses than a pH of 7? Well, if each number is a 10-fold increase, it's 10 times 10, so it would be 100 times greater. 7 to 4, 1,000 times greater. And then the flip side this way here, that as we go towards the basic, the hydrogen ion concentration gets lower. So therefore, a pH of 7 and a pH of 8, a pH of 8 has 10 times less hydrogen ions than a pH of 7, or a pH of 7 has 10 times more. All right, and so that's what that means. So I'm going to show you, this you will not have to calculate on the AP test, but you need to understand the concept of where these numbers come from. How do we know something is a pH of 6? What does that mean? So the equation to figure out pH equals, and it's the negative log of the hydrogen ion concentration. So let me give you an example of something. Let's do pure water as a pH of 7. So a pH of 7 means that it has a hydrogen ion concentration of 10 to the negative 7. That's what these numbers mean. So it's the exponent in the concentration. So the pH would be the negative log of the hydrogen ion concentration, which is 10 to the negative 7. What does that mean, 10 to the negative 7? I'm just going to draw a little arrow here. It means point, and then you do 6 zeros. You move your decimal place over 7, so that point places. So you need 6 zeros, and then a 1. All right, and then this is the molar concentration, meaning that you would have in a liter of water, this is the molar concentration inside of there. That's the concentration of hydrogen ions in 1 liter of the solution. All right, so we're talking about very little hydrogen ions, but it can make a big impact in a cell. All right, and so that's what 10 to the negative 7 means. So if you were to take your calculator and put the negative log of 10 to the negative 7, and put equal, guess what you would get in your calculator? The number 7 would come up. And so that is why a solution that has a concentration of 10 to the negative 7 has a pH of the number 7. All right, and so so that's one example. Let's do example 2. So let's look at a pH of 6. So if I were to ask you, I told you a solution is a pH of 6 and asked you what's the hydrogen ion concentration, what would you tell me? Hydrogen ion concentration would be 10 to the negative 6 molar, which remember that would equal 0.12345 and then 6. All right. So if we look up here, just look at what we just talked about here with going from a pH of 7 to a pH of 6. There's more hydrogen ions, and there's 10 times more, all right, because each one of these numbers represents a 10-fold increase or decrease. Well, let's look at this number. All right, let's look at the concentration. At a pH of 7, this is the concentration at a pH of hydrogen ions. At a pH of 6, this is the concentration. This is a bigger number than this, all right? And and it's 10 times bigger. If we multiplied this number by 10, multiplying it by 10, all right, we would move the decimal place over 1, and so therefore we would have a pH of 6 then, all right? And so that's what this means. So if I were to write it like this about pH of 6, the equation, pH of 6, it would be negative log of 10 to the negative 6, and that would give me 6, and that's how I get that pH of 6. Alrighty, and so that is the pH scale, and our cells are really, really sensitive to changes in pH. And so if we move the pH too much to the left, acidic, or to the right, basic, it can really mess up the chemistry of the cell and really the life of the cell. So therefore, oftentimes in living things, this is our last letter here, letter D, there are things called buffers. Buffers are substances that minimize changes in the H plus concentration and hydroxide ion concentration in a solution. And so I'm going to put here, so we have certain molecules in our body that will help to keep our blood pH level just over 7, so it doesn't really change much. And it does that by either, if your blood becomes too acidic, which means it has too many H pluses, it'll take H pluses out of the solution. Or if it becomes too basic, it has too little H pluses, it will put H pluses in the solution. So I'm just going to put a very common example of this is the carbonic acid buffer system in our blood. In the blood. And I'm going to put here that figure 2.24 shows that. We don't need to know the nitty-gritty of how it exactly works, but that there is a buffer system that works to buffer or resist changes in the hydrogen ion and hydroxide concentration, thereby keeping the pH roughly the same, so that we don't have adverse side effects from the increase or decrease in the hydrogen ion concentration. But if you want to look at the picture, it shows you that. All right. And that is what we need to know about water. So this concludes chapter 2. And so I will end here now.